What happened to Luke? This is still looks like it's looking for a signal. Should we maybe try it again? There we go. Okay, great. All right. So let me start by summarizing what we learned on Monday. We talked about the concept of value and assigning value to stimuli. So basal ganglia, along with the posterior parietal cortex and the frontal lobe, assign value to the available action. So basically, your cortex, in all its glory, one of its jobs is to decide what to do. And the way it does it is by evaluating the possible options and deciding based on its prior history what is the most valuable action. Today I'm going to show you a little bit about the basal ganglia and the way it encodes reward and effort. We tend to produce movements towards stimuli that have the highest subjective value. The relative value of the stimulus affects movement speed. We move faster toward things that we value more. And because time discounts the value of the stimulus, meaning that you rather get reward sooner than later, time discounts the value of the stimulus. The faster we move, the better, because we get our reward sooner. But because you also have to expend energy doing the movement, utility, we think of it as a sum of the gain and the losses of the movement, discounted by time. So we try to attain the most amount of reward while spending the least amount of energy. Okay, so we described an equation, and we described a set of variables that maintained our ideas about energy it takes to make a movement. So there's this concept of reward. You make a movement, you're going to get something good at the end of it, and it has, at least in the case of animals, you can think of it as the energetic value of the food. You can think of that as alpha. So for a lion, eating a gazelle is much more valuable than eating a rabbit. So because he gets much more energy from that large piece of food. Now it's going to have to spend some energy in doing it, and this energy, in the case of a reaching movement, is something that depends on mass, m, distance, d, and time, t. So the slower you move, the longer t is, the less energy you're going to spend. And all of that is discounted by time, 1 plus gamma t, where gamma refers to your temporal discounting. So when we plot such a function, we see that reward gets discounted in time. That's that term alpha divided by 1 plus gamma t. That's discounting of reward. Here's effort, the energy it takes to make a movement. It takes the greatest amount of energy if you move really fast, short duration movement, less energy if you move slow. The sum of these two functions gives you this j, the utility, that has a peak, and that's the best movement that you can make. Now, when we think about increasing effort, when we increase the mass from a small amount to a large amount, what you see in this equation is that this j here, this j is larger for smaller mass than a larger mass, which means that you would rather take a movement that has smaller mass than a larger mass. But if you have to make a movement with a larger mass, you're going to make it slower than you would with a smaller mass. So you not only prefer to move with a smaller mass, if you're forced to move with a larger mass, you will move slower with it. This is what our equations are saying. On the other hand, if we change reward, if we go from a small reward to a large reward, we not only have a greater preference for it, so you see this utility is larger than this utility, so we would prefer to get larger reward than smaller rewards, but you also notice that as the reward increases, the peak shifts to the left, which means you move faster for the larger reward. So you reach faster for the candy that you really like. You walk faster toward the person that you really like. That I don't know if it's true or not. I think it's true that we walk faster toward people I don't like. So basically, what I would suggest to you is that you just stand across Charles and you watch people walk across Charles, and the speed by which they walk, if they're walking toward a person, perhaps is a reflection of how much they care about that person. Okay, that's just my inference about how I think the brain works. All right, so now I'm going to focus on the idea of let's test some of these things in some experiments. So I'm going to look at reaching movements, simple things that you can measure in a laboratory, and use our equations to make some predictions about how people should reach. So the first thing that I'm going to concentrate on is the concept of mass and how mass alters the way you should move. So it turns out that your arm has a particular shape associated with its mass. So if you were to look at how people make movements, ask them to make a single uncorrected movement to a target, say at 10 centimeters. So you put the target anywhere around the circle and you ask them to make a movement. What you see is that some directions they move pretty fast. Here's the peak velocity, about 60 centimeters per second. So over here, they make a fast movement in this direction, but they make a slower movement when it's in this direction. Okay, so your arm is here, I give you a target here, you move pretty fast for that movement, but if I give you a target here, you move pretty slow. Okay, so let me show you how that's related to the mass properties of the arm. So what we need to do is to come up with a set of equations that says what is the effective mass of the arm when it moves in any particular direction. We're going to describe a concept of inertia, we're going to link it to torques that are generated to make the movement, and then from that we're going to come up with a concept of an effective mass. What is the effective mass? And what you're going to see is that when your arm is in this configuration, this movement has a much lower effective mass than this movement. So mass is higher when you move in some directions than other directions. We're going to see how that influences the utility, because remember the utility depends on mass. And then we're going to see, does that alter the duration of the movement? Okay. So we're going to go through some equations to see how to derive this thing called effective mass in terms of our human arm. So here's our coordinate system. There's an X here and there's a Y here. I'm sorry that this screen is so small for this very large auditorium. It's a shame. But you'll have these slides so you can look at it at home. Okay, so there's an X coordinate, there's a Y coordinate. It's focused on the center of the shoulder. So when I ask where is the hand, here's the hand, there's a vector there that points from the origin of that coordinate system to the hand. So you represent the position of your arm using a two-link bar. So here's the first link, here's the second link, right aligned with the forearm and the upper arm. And we can measure the angle that it has with respect to the horizontal line here, and then with respect to this relative axis here. Let's call this theta shoulder, let's call this theta elbow. Okay, so here's the angle of the shoulder, here's the angle of the elbow. Do you see that? Just describing the kinematics of what our arm is. All right, so in order for us to describe the mass of the arm, what we need to know are a number of quantities. We need to know the center of mass. So for each link, there's going to be a center of mass for it, about the middle of it. For the forearm, it's a little bit more toward the hand because the hand is kind of heavy. So it's going to move the center of mass a little bit farther forward. So let's call that lambda. So lambda is this distance from the shoulder to the center of mass of the upper arm. And there's another lambda here from the elbow to the center of mass of the forearm. So there's a length from here to here that tells me the center of mass. There's a length from here to here that tells me that center of mass. It's just a number that tells me the distance. Is that clear? Any questions so far? Okay. Then there's another variable that describes the sort of length of my arm, and here that's represented by d. So I've given you those numbers for a typical human arm here. Distance of the upper arm, and the length of the upper arm and the lower arm, the mass, the length to the center of mass, and this I here is what's called rotary inertia, which is basically the inertia of the arm in measures of, in this case, kilogram meter squared. So these are the quantities that we're going to need to put into a matrix. So in order for me to do that, I'm going to define some intermediate variables, A1, which is in this case equal to the mass of the forearm, A3, which is something like this, and so forth. And the reason why I define these intermediate quantities is because you'll see that when we write the equation for the inertia of the arm, it's going to include these variables. So inertia for a two-joint arm is a 2x2 matrix. And what is this inertia matrix? H, what it's going to refer to is a relationship between torques and acceleration. You're going to present some torques to your arm, and it's going to accelerate. That acceleration is going to be in the coordinates of this theta here. So a torque is going to be a vector. It's going to have some component of a shoulder torque, some component of an elbow torque. That's going to cause motion, and that motion is going to be an acceleration. That acceleration is going to be a 2 by 1 vector. In this case, acceleration of the shoulder, acceleration of the elbow. The matrix that relates torque to acceleration in joint coordinates is h. And it's a 2 by 2 matrix. And it describes basically F is equal to ma, but in the coordinate system of this system. So F is equal to ma is a relationship between forces and accelerations. We're going to write the same equation, but in this case it'll be torques on this two joint arm and acceleration, theta double dots of each joint. And I'll show you what that is. And that's going to be related via mass, and that mass is h. In this case it's a 2 by 2 matrix. And what is it composed of? It's composed of these elements that I wrote here. Okay, so when the arm is in the horizontal plane like this, inertia of the arm is a 2 by 2 matrix like I've shown it to you. Okay, so why do we need that inertia of the arm? What are we trying to do here? So we're trying to write what is the effective mass of the hand. Why is it that my hand feels lighter when I move like this versus moving like this? What I want to do is show you why that is by computing this thing called effective mass. So I've added a couple of more figures here to what we had before. So now what I have is that I have my hand position. That's a vector that points from my shoulder to my hand. I'm going to call that h. It's a vector based on this coordinate system. And then I also have my joint angles, theta shoulder and theta elbow. So over to the right, I now have the forces. I have torque on the shoulder, torque on the elbow, tau s and tau e. And again, I apologize. It's so small for you guys sitting in the back. This is a torque on the shoulder and the elbow. And then I have forces on the hand, fx and fy. So force in Cartesian coordinates, we're going to relate it to torques in joint coordinates. And this relationship is similar to the relationship between position in joint coordinates, theta, that you see here, to position in Cartesian coordinates, the vector h. So the relationship between positions in two coordinate system also defines the relationship between forces in those two coordinate systems. So let's derive this relationship. The first step is to write our vectors. So here's torque. Torque is a 2 by 1 vector, torque shoulder, torque elbow. Theta is position, it's a 2 by 1 vector, theta shoulder, theta elbow. When I write F is equal to ma in joint coordinates, what I'm writing is torque equals to something, in this case h, that 2 by 2 matrix, times acceleration, in this case in joint coordinates, theta double dot. So this is F is equal to ma, but just written in the coordinate system of the joints. The next step is to relate the one coordinate system to another. So at rest, inertia describes the relationship between forces and torques in joint coordinates. And this was what we did in the last slide. We described what h is. Now, what I've done here is write the vector h. The vector h represents, the little h, represents where is hand in Cartesian coordinates. To describe where hand is located in Cartesian coordinates, what I do is describe basically what is this location here with respect to the x and y axis of the hand and the angle thetas that I have. And it turns out, it's easy to show. I can do it for you here. So here's your arm. Here's your x and y axis. And what you want to know is where is this location with respect to these angles, theta s and theta e. So how do I do that? Well, this position here and this position here can be written as follows. So this location, that location up there, is going to be equal to, if this length is d1, if this length is d2, then the x location of my hand is d1 cosine theta shoulder plus d2 cosine theta shoulder plus theta elbow. And this location, its y coordinates, is going to be d1 sine theta shoulder plus d2 sine theta shoulder plus theta elbow. That's a 2 by 1 vector describing my hand position. This is my hand vector in terms of the angles. That's what I've written there. So what I have is a representation of hand position now in terms of joint coordinates. Okay, now what I want to know is what's the relationship between forces and torques? Well, F is equal to ma can be written in terms of the coordinate system that we have as force, which is a 2 by 1 vector, fx and fy, being equal to some matrix M, mass matrix, times the acceleration of the hand. In this case, that's my hand position, so it'll be the second derivative of that vector there with respect to time. So how do we compute that? So what I need to know is what is h double dot and how does it relate to h. So here's h. Here's the vector h. What I want to know is what's its derivative with respect to time. So what I do is to first define the derivative of h with respect to theta. I use the chain rule. So I say, if I want to know what is the derivative of my hand position with respect to time, what I can do is first find this derivative with respect to the angle theta, and then d theta dt multiplied. That's the chain rule. Okay, so what is theta? Theta is this vector, theta s, theta e. So, the purpose of our action here is to understand how torques are related to forces. And to do that, what I need to know is how position in Cartesian coordinates is related to position in joint coordinates. Once I describe that relationship, then what I need to know is how the derivatives of position in one coordinate system are related to the derivatives of position in another coordinate system. So how do I find the derivative of position with respect to time? What I do is define dh dt to be dh d theta dt. So here's h. What do I mean by dh d theta? What I do is dh d theta is equal to the derivative of h with respect to theta s and derivative of h with respect to theta e. That's the derivative of that vector. That's one component of it. It's a 2 by 1 vector, so what I need to do is, let's define this as, this is a vector, so I'm going to call this hx, hy. So it's going to be dhx d theta s. That's this term here. And then the second term is dhx with respect to d theta e, dhy d theta e, dhy. There we go. This is what I wrote here. dhy d theta s, dhy d theta e. This is what we have here. So we get a 2 by 2 matrix that defines the derivative of my 2 by 1 vector with respect to this theta, which is position. So this becomes a matrix. This is called a Jacobian matrix. This, gamma, is a Jacobian matrix, which what it's doing is finding the derivative of one coordinate system with respect to another coordinate system. It's saying basically, when there's change in one coordinate system, how does it affect the position in another coordinate system? All right, why do I need this? Because what I want to know is that how does F here relate to theta, to that torque angle up there? And to do that, what I need to know is that how does H double dot relate to theta double dot? So what I've done first is to find dh d theta. When I have dh d theta, then I can use this equation, right? So I can find the derivative of h with respect to time by multiplying dh d theta times d theta dt. That's what I've done here. Okay, so my objective is to relate one coordinate system to another. It turns out that torques are related to forces by the transpose of this gamma matrix. What was gamma? Gamma was our Jacobian. It's this term here. This is a gamma. This 2 by 2 matrix. The transpose of that allows me to go from forces in one coordinate system to forces in another coordinate system. In this case, force in Cartesian coordinates to torques in joint coordinates. Okay, so I have hand position as a function of joint angle. What I can do is write the derivative of hand position, dh dt, that's h dot. See, h dot over there, this term here, h dot, that's dh dt, is equal to dh d theta, that's this gamma function, this is dh d theta, times theta dot, that's velocity. So that's the relationship between the first derivative of position in joint coordinates to first derivative of position in hand coordinates. But what I need is the relationship between accelerations, because I need h double dot. So I find the derivative of this term again. So that becomes the derivative of the first term, d gamma d theta, times theta dot. Why is that? Because I want to know what is d gamma dt. That's equal to d gamma d theta times d theta dt. So that's d gamma d theta times theta dot, and then times theta dot again. That's the term that remains, plus the derivative of the second term times the first term, which is gamma times theta double dot. So h dot is equal to gamma theta dot. H double dot is equal to derivative of the first term times the second term. That's here, d gamma d theta times d theta dt times theta dot, plus the first term times the derivative of the second term, gamma times the second derivative of theta d theta dt squared. That's this equation that I wrote there. Okay, let me stop for a second. Let's see where we are. Any questions so far? We're just taking derivatives of vectors. Nothing out of the ordinary so far. But why are we doing it? Because what we want to know is what's the relationship between torques in one coordinate system to another. Well, I have two equations now. I have torque is equal to mass times acceleration in joint coordinates. I have torque is equal to transpose of the Jacobian times force. And so I put those things together and I get h theta double dot is equal to gamma transpose times F. So now what I want to know is that what's the relationship between forces and hand acceleration. And so this term here, I simplify and I get an approximation that says basically force is equal to m times h double dot. Acceleration of the hand is related to forces in the hand with this matrix M, where M is this relationship, is the inverse of the Jacobian transpose times h times inverse of the Jacobian. So it's Jacobian inverse transpose times M, this term here. So if we have h, which we had from a couple of slides ago, and if we have the Jacobian, we can compute what mass matrix is, and that tells me how to go from acceleration in the hand to forces in the hand. So we started out in joint coordinates. We defined an inertia, which we called h. That told us how to go from accelerations in joint coordinates to torques. Then what we did is we went through some calculations to compute how do we go from accelerations in hand coordinates, Cartesian coordinates, to forces. We get this matrix called M, and now we have a relationship between the mass matrix at the hand and the inertia matrix of the joints. So now what I'm going to do, I'm going to use that to compute the relationship between forces that you need to produce to make a movement in Cartesian coordinates and accelerations of the hand. So what we have is this inertia that goes from joint coordinates to mass coordinates. So M is going to be a 2 by 2 matrix. Okay. All right. So this is now what I have. I can compute M. What we do is that I pick a unit length acceleration in direction p. So you just say, I want to accelerate my hand 1 meters per second squared in any direction. Take that and tell me what is the force that I need to produce. So here's an example. So here's your arm. Say you want to accelerate to the right by 1 meters per second squared. That's h double dot. You can multiply that. So here's h double dot. Multiply that by your M matrix. This is a 2 by 1 vector, is h double dot. M is a 2 by 2 matrix. Multiply that and you get a force, which is a 2 by 1 vector. Here's the force that you get. So you notice that the force is not in the same direction as acceleration, because the arm is a complicated structure. It is not a point mass. It is a large structure that has its center of mass at various locations. What we are able to do is to tell you that in order for you to accelerate this way, you have to produce a force this way. Now, if you wanted to produce an acceleration at a different direction, say at 45 degrees, you notice that the force becomes smaller. And now if you want to produce an acceleration at 90 degrees, you notice that the force becomes larger. So for some directions, you need a very small force, like you see here. For other directions, you need a much larger force. Now what we're going to do is sum up, basically add up all of those vectors f. So as you take a hand position, let's see if I can draw this for you. Okay, so here's your arm. You're sitting there. You generate a acceleration in some direction. Let's call that h double dot. And what we're going to do is we're going to vary this along a circle. For every one of these vectors, we get a force vector. You get a force vector like this for this one. And then for this acceleration, I get a force vector like that. So now if I were to connect these forces for the various h's, so as h goes around the circle, I draw a vector force that I need to produce. And if I connect that, I'm going to get an ellipse. It's going to look like this. That's what's shown here. What this says is that you have a large effective mass in this direction, you have a small effective mass in that direction. And you can feel it. You can move your arm here, it feels heavy. Move here, it feels light. That's just the effective mass of your arm. Why is this useful for us? Well, because remember now what we want to do is we want to go back now to our problem. Why is it that people move so much faster when they're asked to move over here than in this direction? They move much slower because of their effective mass. They're moving a lot smaller mass in this direction than in this direction. Okay? So we go back to our utility. Our utility says that there's a reward here and there's a mass that you have to move. Well, your mass is small in this direction, large in this direction. So if we just put that in our equation, we can compute how much time it takes to make a movement. For each direction of movement, we compute this optimum t star. So that was the optimum value that makes this utility the highest possible. We vary m in various directions, and we ask, does that produce for us the movement? And indeed it does. So you can see that duration of the movement is longest in this direction, and it is shortest in this direction. Why? Because mass is largest in this direction and smallest in that direction. And so if you have to move 10 centimeters, if your duration is larger in some direction, it means that you're going to move slower. Peak velocity is going to be smaller, larger in other directions. Let me stop and see if there are any questions. Yeah?
So little f, is that
in Cartesian coordinates.
What's the joint force?
Tau. Yeah?
Why is the force curve different from the duration curve?
The what curve? Oh, why is the force curve different than the duration curve? Because the duration curve has this square root in there. So, you know, mass is changing. It's small and it becomes large. And so T star is telling you in each direction what's the mass. So small direction, small force, small mass, large mass. And so T star becomes, as mass becomes smaller, T star is smaller. You move more quickly. As mass becomes larger, it increases. So as mass becomes smaller, this moves towards 0.
And how did you get that equation before the optimum?
Right. So on Monday, what we did is that we said we want to find the optimum utility. So what we did, we took the derivative of the utility with respect to t, set it equal to 0, and we found this equation. So this is the time, the duration t, that maximizes the utility. This is the, here, if I go back here now to, let me show you where we were. So this is this time as a function of m. The peak location of that curve is at the location where the derivative is 0, right? So you find the derivative of this function with respect to t, set it equal to 0, solve for t, that gives you this equation. That's the duration that maximizes the utility. Okay. All right. So we have a mechanism by which we can predict how long people will take to make a movement if we knew what they mean, what they represent as reward as we change mass. So now the next question is, all right, it should also tell us what they would prefer to do. So they should prefer to move with a smaller mass than the larger mass. That's the utility. So if we go back now and ask, well, which one should they prefer to do? Should they prefer to move with a small mass than a larger mass? They should prefer to move with a smaller mass. So if you take your arm and if you draw the mass matrix, which is what is shown here, you see that for your left arm, the mass matrix looks like this. For your right arm, it looks like that. It's along the forearm. That's when you get the largest mass. So basically, if you had the option of choosing to move in any direction, so you could move like this, you can move like this, you can move like that, you should prefer to move like this because that has the smallest mass, as opposed to this, which has the largest mass. So if utility is a way for us to understand the value that the brain assigns to a movement, it should prefer to move basically in directions that are less costly. That's the direction that has a smaller mass. For the right arm, that's this direction. For the left arm, that's this direction. So in an experiment, people asked individuals to reach in any direction that they chose. Out and back movements, constant amplitude. And they measured the probability of reach direction. And here's what they found. So for the right arm, it tended to move like this. That's the greatest probability that you see here. And less in that direction. But for the left arm, it was opposite. More in this direction, less in that direction. So if you take that utility function, J, and you just plot it as a function of direction of movement, where direction is represented by mass, what you see is that you have the maximum utility in the directions where you pick most oftentimes. So the choices that you make in terms of which action to perform seem to relate to the utility associated with it. So energy and reward together give us a sense of which action to perform as well as how to perform it. Let me stop to see if there are any questions. Yes, sir.
In your equation for J, why is it okay for you to make the assumption that alpha and M are independent?
Alpha and
M
are independent? So mass is something that just depends on your body, right? You can't change it. Alpha depends on the environment. What are you moving for? What are you moving toward? So that's like the experimenter deciding that for you to make this movement, I'm going to give you a cream puff versus a Snickers bar. And you know, whichever one you value more, it depends on you, how hungry you are and things like that. Are you lactose intolerant, whatever. Okay, let me summarize. The utility of a movement is the sum of gains and losses of that movement discounted by time. Increased reward results in increased utility, making that action more preferable. Movement speed is higher toward things that we have greater reward. Increased mass causes the utility to become smaller and also makes the action less preferable. Okay, so if the effort that it takes to make a movement depends on the energy it takes to move, what we can do is to simplify things, and let's just imagine you don't have to move at all. All you have is the constant force to produce, isometric force. And let's ask, can we understand the choices that people make based on the energetic cost of making that choice? So let's just look at isometric forces, producing constant force. So in this experiment, what was done is that they stimulated the muscles. So they stimulated for half a second, 1 second, 1.5 seconds at 20 hertz versus 80 hertz. So at 20 hertz, the muscle produces a little bit of force and then it falls off. And at 80 hertz, it produces more force and it falls off. So you can stimulate the muscle and see how much force it produces. At the same time, they measured the metabolic energy that was being spent by the muscle. So in this case, they measured ATP that was consumed by that muscle as it was being stimulated. And that's shown in this figure here. So 20 hertz stimulation for half a second and 1.5 seconds and so forth. You see that as the stimulation period increases, the energy that's consumed increases. For 80 hertz, it's greater than at 20 hertz. So let's suppose that what we have is that the force that's produced by the muscle is this exponential function. So here's, it rises up and then it falls. And now ask, well, what's the energy that it takes to produce this force? It turns out that a simple way to relate these is to imagine that the energy it takes to produce force as a function of time is just the integral of that force. So if you integrate the force as a function of time that you're producing it, it produces a relatively good estimate of the energy it takes to produce that force. So the integral of the force that's being produced is a reasonable measure of the energy it takes to produce the force. This is in an isometric condition. Sum of the force is basically a reasonable estimate of the energy it takes to produce the force. And indeed, there's this really nice relationship between the integral of the force that you're producing versus the energy that's consumed, the oxygen that's consumed to produce the force. Okay? So that gives us a way to think about how much energy it takes to produce force. Now let's ask, does the brain think about effort in terms of these energetic values associated with producing force? So I'm going to describe for you an experiment on perception of effort. How do you perceive how much effort are you putting into something? So here was our utility function. We had reward. And now what we have is effort, which is basically the energy it takes to produce something. So in this case, it's an isometric task. You're just producing force against the transducer. And so the energy that it takes is a function of that force that you're producing. And then you are discounting it in time. So here's our energy function. And suppose that the task is very simple to produce just a constant amount of force F. In which case, the integral here is just is only going to become F times t. So this is the energy it takes to produce that movement. The utility of that action, of the force, is just E divided by 1 plus gamma t, which is shown here. And so if you're producing constant force, then that just becomes F times t. So if the force that you're producing is this, with a magnitude F, duration t, then the integral of that F times t. That's going to be the energy proportional to the force that you produce. That's shown here in the numerator of this equation. Okay? So the effort it takes is proportional to the energy it takes. And if you're producing a constant amount of force, it just is the integral of that, which is F times t. All right. So if you look at this, there's something interesting that happens. It says as duration of the force production increases, as t increases, numerator increases, of course. But if you pay attention to it, you notice that it doesn't just continue to grow. So if I ask you to produce 10 newtons for 1 minute, you produce some amount of effort. Now, if I ask you to produce 10 newtons for 2 minutes, this discounting function is going to make it so that the effort doesn't just keep on growing, but it's going to reach an asymptote. And I'm going to show you what that means. So the idea is that if this is how your brain measures effort, then perception of effort should become indifferent to duration of force production as duration increases. Basically, for you, the effort associated with producing 1 Newton of force for 1 minute is much less than 1 Newton of force for 2 minutes. But 1 Newton of force for 100 minutes is only a little bit different than 1 Newton of force for 101 minutes. So the difference between 1 minute and 2 minutes is a lot. But the difference between 100 minutes and 101 minutes is very little in this world. Even though the mathematical difference between those is the same, 1 minute. But if the perception of effort is based on this discounting of the energetic costs, then for us, 1 minute will be very different than 2 minutes, but 100 minutes will not be that different from 101 minutes. Let me show you that. Okay, so we're going to look at an experiment. In that experiment, they asked people to produce force F1 for period T1, and then force F2 for period T2. So they asked you to produce 10 newtons for 1 second versus 5 newtons for 2 seconds. F1 T1 versus F2 T2. Then they said, all right, after you produce that force, tell us which one you'd like to do again. And presumably you'd pick the one that was less effortful. Okay? You repeat this, and until you find that what is the indifference point? At what point is F1T1 roughly equal to F2T2? And so let's write down our equation. Let's see if we can understand what that means. So the utility in terms of the force, the reward is the same, so we can just forget about alpha. The effort is the only thing that matters. There's F1T1, so here's the effort it takes to produce it, and here's F2T2, and at some point, the effort it takes to produce F1T1 is going to be equal to F2T2. So these two equations are going to be equal. For you, the perception is the same. The effort it takes to produce F1T1 is the same as F2T2. Now, if you solve for F2, what you notice is that you get a relationship whereas T2 goes to infinity, F2 doesn't go to 0, but it goes to an asymptote. What this means is that as F1T1 is kept constant, F2 is going to be varied by T2. T2 is going to become longer and longer and longer. So produce 10 newtons for 1 minute versus 5 newtons for 2 minutes, 5 newtons for 3 minutes, 5 minutes, 8 minutes, an hour. What you see is that the equivalent point, meaning that the amount of effort that I constitute for F1T1 doesn't go to 0 as T2 goes to infinity. What this means that as duration of T2 increases, F2 doesn't go to 0, but approaches a plateau that increases with F1. Let me show that to you graphically so we can understand the implications of the theory. So suppose that the way your brain measures effort is to say, let's look at the force time integral, which is shown here. 20 newtons for 0.5 seconds. 20 newtons for 0.5 seconds. The integral of that is the area under the curve, right? But if we discount it by time, we can compute what's the equivalent perception for us in terms of effort if I now alter the magnitude of the force and its duration. So if this is 20 newtons for half a second, equivalent perception of force for me would be for 1 second, 13.3 newtons. For 2 seconds, it'll be about 10 newtons. For 4 seconds, it'll be about 8 newtons. So you notice, as I increase time here, this doesn't go to 0. It reaches a plateau. For me, this is the same effort as this, even though the integral here is much larger. Why? Because time discounts my effort. I'm dividing it up over a longer period of time. And what that means is that equal utility lines don't go to 0, but they reach a plateau. That's what the temporal discounting means. If you take effort, a large effort, and you divide it up over a long period of time, then it's somehow much more palatable, as you can see here. So this amount of effort is equal to this amount of effort, even though this is for a much longer period of time. So 20 newtons of force held for half a second is equivalent to 15 newtons of force held for 3.5 seconds, even though it takes much more energy to produce 15 newtons of force for 3.5 seconds. Why? Because I'm discounting it in time. I'm dividing it up over all this period of time. That makes it so that the perception of effort becomes equivalent to me. So this is what the theory says. So let me show you what the experimental results show. So here's what people did. And what they did is that for them, 20 newtons or so was this much effort. The same amount of effort is out here. You notice that these lines are flat, which is telling us that perception of effort doesn't go to 0 as you increase its duration, but it reaches a plateau. Because long durations of time, 100 seconds, is almost the same to us as 101 seconds, whereas 1 second is very different for us than 2 seconds. So if you have to wait a week for something, waiting another day is no big deal. But if you have to wait 2 hours for something, waiting another day is a huge deal. Okay? You discount things with time, and that makes it so that effort is, results in these indifference curves. So the force time indifference curves that people exhibit shows a curious pattern. Perception of effort plateaus despite increased duration of force. This pattern is consistent with the idea that just like reward, effort is discounted by time. Okay, let me summarize where we are. The metabolic cost of force production appears to grow linearly with the integral of force. The utility of an action discounts effort by time. This means that if effort is related to metabolic cost of force, then its utility is temporally discounted. This makes the unexpected prediction that perception of effort doesn't increase linearly, but we should rather produce a small force for a long time than a large force for a short time. Okay, let me stop for a second and see if you have any questions. Time discounts reward, but also discounts effort. So the reason for that may be that in our brain, there are neurotransmitters that encode reward and discount it, and the same neurotransmitters encode effort. And perhaps because of this similarity between the mechanisms of representing reward and effort, we get temporal discounting of both of these. And the central idea there is that it is the basal ganglia that is responsible for much of this representation of effort and reward. And that's why in individuals that suffer from basal ganglia disorders like Parkinson's disease, what you see is not just a change in the choices that they make in their lives, but also in how they move. So it's not that they can't move fast. It's not like if there was a fire alarm, they would get up out of their seat and run out the door. But at the most conditions that you and I face, they simply don't move fast because it just isn't as rewarding as it might be for another person, a healthy individual, because the neurotransmitters that represent this have changed. Okay, so the last part of the lecture, I'm going to keep you here for about 5-6 more minutes to show you how dopamine represents reward and effort. And to do that, I need to describe for you what is dopamine and where is it released from. So dopamine comes from neurons that have their cell bodies in the brainstem, in an area called substantia nigra. This is a part of the basal ganglia. They project to 3 main areas. The striatum. The striatum is part of the basal ganglia. That's the input stage to it. The limbic system, that's your hippocampus and your medial temporal lobe, and your prefrontal cortex. Basically, dopamine, its largest projections is to the striatum, which is the basal ganglia. So how does dopamine respond to reward? To show you that, I have data here from Wolfram Schultz. This is data from monkeys, and it looks at what happens to dopamine when an animal is shown a stimulus that predicts reward. So this is a dopamine neuron in substantia nigra. And this time here, at time 0, the animal is shown a stimulus. That stimulus is going to predict reward. So in this case, the animal is shown that stimulus, and this stimulus says you're not going to get a reward for this. This stimulus comes on, and the animal understands that he's going to get about a quarter of the times he's going to get reward. In this case, half of the time he's going to get reward. In this case, all of the time he's going to get reward. So what you see is that the dopamine cell doesn't respond when he's not going to get reward. It responds strongly when, for sure, he's going to get reward. So what we see is that as the probability of reward increases, the cell that is responding to that probability is responding stronger. When the probability is high, the cell responds strongly. You get a lot of dopamine when a stimulus comes on that says, I'm going to get juice, in this case for the monkey. Presumably that's why, when you see a face, when you enjoy a moment, it's because dopamine is your brain saying, that was good, I like that stimulus that came on. It's very liberating to think about the brain in terms of these neurotransmitters. It just takes out the whole mystery of psychology and just the sum of that framework. Okay, so dopamine responds to reward. Things that it values more, you get more of that, and things that you value less, you get less of that. And so Parkinson's disease kills these cells. These cells that are so important for telling you when something good is happening, Parkinson's disease kills these neurons. Okay, so it turns out that it's not just reward that dopamine responds to, it also cares about when you're going to get the reward. So in these experiments, what we're going to look at is a condition where the monkey is trained so that when he sees a stimulus, he knows he has to wait 8 seconds to get the juice versus a shorter period of time. And let's see how dopamine responds to it. So the animal is going to see a stimulus, and that stimulus is going to tell it after a short delay you're going to get juice, and these animals are thirsty, versus getting another stimulus that says, no, you're going to have to wait a long time, and in this case, you're going to get a large amount of juice. So if you look at how the stimulus produces dopamine response, what you see is that if the stimulus goes on here, and you're going to have to wait a short time to get the juice, you see that the response is higher than if you have to wait a long time. So the response takes into account how long you have to wait. It's not just that you're going to get 3 drops of juice. If those 3 drops of juice are going to come soon, that value is higher, and dopamine gives you a greater response. So you see how disorders in decision making and impulsivity and issues with compulsive behavior, it could be linked to dopamine. If dopamine is telling you this thing is valuable, you can't help but say, I want it. And if it says this thing is valuable no matter what, then people do crazy things. They become addicted. You know, they're willing to throw away their lives in order to do what? To get dopamine. So you see these temporal discount functions in the dopamine release. Discharge with respect to baseline when the stimulus comes as a function of delay to reward. You see, if you're going to get this large amount of juice now, there's a lot of dopamine release, but if you see that stimulus and says you're going to have to wait to get it, then the dopamine response is lower. That's why you would rather get $10 today than $10 next week. Why? Because $10 today for your brain produces greater activity in your dopamine system. It says, this is what I want. Now, it's probably likely that there's other neurotransmitters that are involved in this, but right now what we understand is that so much of it depends on this neurotransmitter that's released in the substantia nigra affecting your basal ganglia. All right. The final point is that most of the same cells that release dopamine and are engaged by reward, they also care about effort. So you see that effort relationships and reward relationships are intermixed with this dopamine signal. In this experiment, what happened was that the animal had to move to get reward, but sometimes had to move against a heavy load, push hard to get the reward. Sometimes had to move against a light load to push and get the reward. Obviously, the animal would have to produce greater effort sometimes than other times, and sometimes would get large reward, sometimes would get small reward. So what they did is they looked at how the cellular activity changed. So they found that there were some dopamine cells over here, this black one, they only cared about reward. They didn't really respond to whether there was going to be high effort or low effort. But there was a group of cells, this pink one that you see here, that encoded both reward and effort. And we'll see an example of that in this slide. So this is a cell that cares only about reward. So the stimulus goes on here, and sometimes you're going to have to make a movement with low reward and high effort. On the other hand, you can make a movement that has high effort and low reward. And what you see here is that what matters for this cell is that the reward size. As reward size is increasing, what you see is that the activity in the cell is increasing. It doesn't care that it has to produce a small effort or a large effort. In both cases, its activity is the same. So this cell doesn't care about effort, only cares about reward. Most of the dopamine cells only care about reward. Some of them also care about effort. Now what you see here. So this cell generally fires more when there's greater reward, fires less when there's less reward, but you see there's some effort modulation. So it likes it when it gets that large reward with small amount of effort, and likes it less if it gets that large reward with a large effort. So this cell cares both about reward and effort, whereas this cell only cares about reward. Most of the cells look like this. They only care about reward. Effort seems to be only a fraction of the cells in the basal ganglia. So I will just end with linking this for you to 2 prominent diseases that affect the brain. One is Parkinson's disease. In Parkinson's disease, dopamine neurons die. It's a degenerative disease, so people continue to lose their dopamine cells. So when surgeons go in the brain and insert a deep brain stimulator, what they're doing isn't replacing the dopamine cells, right? So there's no way to stop the loss of dopamine. But what they're doing is that they are affecting the symptoms of dopamine loss by going and disrupting another brain circuit. By getting 2 disruptions, you are improving the motor function of the individual, but you're not really replacing dopamine in any way. The dopamine replacement comes from the drugs that the people take, L-Dopa and so forth. So the symptoms of the disease are slowness of the movement, called bradykinesia, tremor, and rigidity. Slowness of the movement in particular appear to be context dependent. So when a Parkinsonian patient it moves slow, it's not that they can't move fast, it's just that under most conditions they don't want to move fast. It's as if it causes too much effort to move fast. But if their life depends on it, they're willing to move fast, and in that case they do so. So treatment includes dopamine replacement therapy. Schizophrenia is another disease that affects the dopamine system. Symptoms include hallucinations, delusions, unrealistic beliefs like superpowers. And pharmacological treatments include dopamine antagonists. They block dopamine. It's as if you have too much dopamine in schizophrenia. And a component of schizophrenia appears to be an overacting dopamine system. So too little dopamine seems to give you Parkinson. Too much dopamine seems to give you schizophrenia. Sorry to keep you longer than usual. Thank you so much. I'll see you in a while.